Hi, and welcome to Talking Tech. I'm your host, Alejandro, and I had the great pleasure to meet Arik and Yaron, who are the lead engineers who have been working on Intel's latest processor, Lunar Lake.
So I'm a Lunar Lake lead architect. I'm actually managing the SoC architecture team in IDC that works on the SoC definition for the client products, mobile as well as desktop products.
I'm today the general manager of the client organization in Intel. Was also the Lunar Lake design manager. And this is my role. We are creating the good products for the PC market.
So let's start talking about Lunar Lake and kind of what do you guys have in mind when you were first designing it? So for example, when we're doing a Raptor Lake and Alder Lake, we're thinking about like, hey, these two architectures or processors are going to span like mobile and desktop. What was the thought behind when you were designing for Lunar Lake?
When we started to design Lunar Lake, we had in mind that we need to be more power efficient. Okay? And we also wanted to target to the low power envelope, to the low power segment. And we said, let's think out of the box, what do we do to reduce power? In this in mind, we look at all the vectors, how to do power efficiency, how to reduce the power, how to optimize, how to build a customized product, and not just try to scale it up to all the segments, like from desktop to the, 65 watt to the 8 watt. So this is what we wanted to achieve, and we worked hard, to make it happen.
Usually, when I did Alder Lake back then, we started with desktop and then we scaled down to the smaller, low power parts. But in Lunar Lake, it was different. We wanted to aim specific power envelope. We started from fanless, then a bit more than higher power envelopes. And it was a dedicated part for this segment, and we wanted to make it best in class.
We want to build a premium, low power, optimized product.
What were the goals? So you said for a premium low power, what are kind of the things that when you sit down with the fellow architects and designers, like, all right, these are kind of our goal, then what do we have to do to reach that goal?
So first of all, it's to identify every transistor that is not needed to be removed. It's in high level. And not to have a superset product, so it's really customized. Usually we are not doing that, so we did it in Lunar Lake.
First, we said it's a premium part. Mm-hmm. So everything there is premium. We'll put the best graphics, we'll put the best AI engine, the NPU. Our cores will be optimized for this specific usage, for specifically lighter usages. And we'll have a significant improvement in power consumption, which will lead to much better battery life. And we want all of it to be working together as a single piece. Together with that, we added memory and package to have best DRAM consumption, as well as a luxury in the power delivery rails with the new PMICs on the platform, on the motherboard. So they can deliver the best rails that we can supply the chip. So it will be very power efficient.
You added the DRAM in there to keep the power lower. Why is it lower when you have it on package?
The footprint is much smaller. So the lines are very short, and then you consume much lower power because you need to route much smaller distance.
So smaller distances, that means less power to send the signal and reach that.
And it's also optimized just for this specific DRAM types. Yeah, so the PHY could be much better.
Okay, so it's a specific RAM that we're optimizing for.
Correct.
Basically, with this memory and package, we could achieve 40% PHY power reduction. And also the short traces are enabled to meet the higher frequency with less effort, let's say.
Yeah, okay. Yeah, that makes sense. So PHY is the physical layer in which we actually transmit. Mm-hmm. And so saving 40%. And like you said, because you have shorter traces, you have higher speeds. So what speeds are we able to reach now on Lunar Lake?
We can reach up to 8.5 gigatransfer per second, which is an impressive number.
That is, yes. Yeah, that is pretty impressive. So for Meteor Lake, we had 4 different tiles. How does it look like for Lunar Lake? How many tiles do we have in Lunar Lake?
In Lunar Lake, we have two tiles. The big one is the CPU tiles, and we have the PCD tiles. So we try to reduce the number of tiles, of course, to increase the power efficiency.
The compute tile puts together all the XPUs, all the compute engines. So the cores, it has the graphics, it has the NPU, it has the imaging, it has display and media as well. And together with that, the memory components, the memory subsystem, the caches, the memory controllers, the DRAM PHY, all of it together makes it very optimized and efficient.
Before we kind of dive into each one of those blocks, in Meteor Lake, we had those spread across different tiles. What was the reasoning of bringing all those back to just one compute tile?
Yeah, first we wanted to put all the elements on a leading process. It was very important for us. We wanted to get the best for those transistors. This means that it will be optimized in power. They will get the best speeds. And the second was to optimize latency. Latency is important for performance. And therefore, if they all reside together, we can get the best latency possible can get.
So let's talk about the different blocks, the different XPs they have in there. So we have, I guess just like we had before, we have performance cores and we have E-cores. Let's talk about the performance cores. How many are they? What have they changed?
Yeah, we have 4 P-cores, 4 performance cores. It's a new Lion Cove core. The big thing there is that it's a single-threaded core. It has only one thread, but it's improved in its IPC. It also improved its performance per watt per area because it's a single-thread core. It has a bigger cache, and it also resides inside the LLC structure, same structure as we had in the past, which boosted even more in terms of latency and performance. Overall, a very powerful unit.
And the reason that it's, see if I understand correctly, the reason that it's just single thread is because we were designing for a better PNP power performance, right?
That's correct. And when you look on the evolvement of the hybrid architecture, we started in Alder Lake in a performance hybrid architecture. Now it's a bit different. The hybrid evolvement led us to a thought that we don't really need the single thread, the SMT support, the hyper-threading support inside the B core, because we actually scale in multi-thread using more and more E-cores as we go up in the power envelopes. And therefore, it makes sense to go with a single-thread performance core that is optimized, while if you want to scale to more threads and have higher multi-thread performance, you just add more E-cores.
Okay.
And this hybrid architecture is a bit different in a sense that the efficient cores, that maybe we'll talk about them, are much more performance capable.
Right. That's actually what I want to touch on. So just because the fact that they're called efficient cores doesn't mean that they're less powerful than the P cores. Actually, there's a lot of changes that you could probably let us on into these.
So, efficiency is the amount of performance you can have per power envelope. So performance per watt and efficiency is somewhat the same. And indeed, the efficient cores are increasing their performance, and they are also improving their power, and therefore their performance per watt is better. When you have a power limitation, if you're better in efficiency, if you're better in performance per watt, your absolute performance that you can get to in a specific power envelope is higher. And this is why they are efficient core. They are also outperforming the P cores if you go to low power envelope. Okay, and that's something that we actually use quite a lot in Lunar Lake. We want most of the usages to be used by the efficient core because you usually need casual type of performance. While if you really need some intense workload performance, then you switch to the P cores and you get those peak performance numbers.
And can you tell us a little bit more about some of the changes? Because I know maybe like we had the E cores. But there were some on the compute tile, and there were also some other ones on the SoC tile on the low power island, and there has been some changes to that.
Right. So Meteor Lake had 3 types of cores. They had in the compute tile, they had the B cores, the performance cores. They have the E cores also resides inside the compute tile together with them on the same caching structure as well as the fabric. And they had the low power island, which is yet another flavor of the E-cores, which were aimed for low power. We actually changed the concept a bit. First, we only have performance cores residing on the big cache structure with the ring. And the second, we took the low power island and we improved it to still work in low power, but to also scale to high power envelopes and be much more efficient. We did a couple of things. We changed the structure from 2 cores to 4 cores. We increased the cache from 2 megabyte to 4 megabyte. We added a memory side cache, which contributes a lot to the instruction per cycle of the E-core, because it's yet another cache that the E-core can use. And we added dedicated power delivery, so you could shift the voltage and frequency of the E-cores separately from everything, separately from the other cores or from the GPU or NPU or the memory subsystem. And the last thing is that it's on a leading node, so it gives the value as well. So all of those things makes the E-cluster, what we call it today in Lunar Lake, which was previously low power island, a much more efficient structure.
Okay, so what is the main idea of separating the performance cluster and the efficient cluster?
The main idea of separating them is that in Lunar Lake, we created a strong efficient cluster that is doubling the frequency, doubling the number of cores, and also putting it on the compute tile on a leading edge process. And once you have this strong efficient cluster, you can run a lot of application on this cluster, which connected directly to the interconnect, what we call network on a chip. And on the other side, you have the P-core cluster, which connected to a ring, which is more power consuming, that you can use for more performance demanding application. So the main idea is to try to run most of the application on the efficient cluster and save the power of the P-core cluster. And only when you need performance, you will activate the P-core cluster. And this is one of the big things that we did in Lunar Lake.
And I guess that's kind of one of the reasons why the microarchitecture on the E cluster was completely revamped, and there were so many changes done.
Correct.
That way, so you can have more workloads being run on that than having to go and activate the P-core.
Correct. Every time you activate the P-core, you consume the ring fabric and the power. So basically, you need to do software optimization, hardware optimization to make it efficient. But once you have the good recipe, you know how to control, how to run a containment of tasks to the E-core cluster, and the performance demanding task will go to the performance cluster.
So besides the L2 within the E-cluster cache, that side memory cache is completely new.
Yes.
And the reason, if I understand correctly, that it saves us a power is because we have a bigger cache, so it saves us the amount of, we wouldn't have to go to the DDR anymore and fetch the data.
Correct. So similar to other caches, this is a memory side cache, so it works a bit differently, but it does similar things. So first, it's close to the silicon, so the latency is much better, so you get more performance. And the second is by accessing this cache, you do not go out to the DRAM, so you also save power.
In Lunar Lake, we did it for the first time. We have the hardware, we have the capabilities. It requires software optimization, of course. So this is something that we see benefit from it.
Can it only be accessed by the E-cores, or can it also be accessed by other blocks?
No, it can access by other blocks, and actually it's used by other blocks, like the other engines, like the AI engines and the media engines. We do leverage it for buffering and reduce the access to the memory, as I said.
It is accessible by any agent in the system. It's not valuable for any agent in the system. Therefore, we are doing some cache ways allocation, dynamic cache ways allocation, in which we can allocate some ways for a specific engine when we find it beneficial. So we allocate some of the ways to the Atom cores or to the E-core cluster. We allocate some for the P-cores. We allocate some for media, and it's dynamic. It does contribute the E-core cluster more than it contributes the P-core cluster, and it does also contribute some devices as well.
That's pretty amazing because you have to do all this traffic controlling, like traffic of like, okay, who's going to access the memory and who's going to be able to fetch the data and retrieve the data. So that seems like it's a very complex, which is pretty neat.
Yeah, it is. It is what we did for the first time. It is complex, and again, we are working to improve it as we go.
You were mentioning when we were talking about the E-cores clusters that you can actually turn it on or off. So does that mean that it has like its own power rail?
Yeah, as I said, one of the changes that we did is that it has an independent power rail. And this is what actually the PMIC allows us to do. So you're connecting a completely separate rail. It's only for the E-core cluster. Then you turn it off completely, yeah, including its cache, while the P-core can work. Same goes vice versa. You can completely turn off the P-core cluster and let the E-core work efficiently. So you do not need to pay for the leakage or the power of each of the blocks while you're working. You also can flush those caches in each side, and therefore it's more efficient.
So how many other independent rails, voltage rails we have there?
Oh, we have quite many. I think it's a record in Lunar Lake.
Okay.
We have like more than 15.
But the major ones, I think, because there's four PMICs, right? So which one those control?
So the big ones are, we have the P-core, we have the E-core one, we have the system agent one, and we have the graphics. Those are the four big ones.
Okay.
Except for that, we have plenty of others. We have also added variable rails, not only fixed rails. So for example, the Atom rails is variable. We added some variable rails for the DRAM itself. We wanted to make everything efficient. So the PMIC allowed us to add those capabilities. Therefore, it's premium.
These PMICs allow us better resolution, better accuracy in the voltage supply, and also give us the flexibility to have a luxury of rails. So we're also using the telemetry indication to control them and consume power more efficiency. So basically, this is why we use the PMIC. Again, for a premium product, power efficient product, energy efficient. That is the main purpose.
And who you said that from the telemetry? Who's providing the telemetry or who's controlling?
The PMIC itself. The PMIC chips supports telemetry that we read them and use them for controlling the power resolution better.
And that way, so 4 PMICs for 4 different power rails, so you can actually turn on and off or provide more accurate or different voltages, so you can have a better power savings.
Correct.
Let's change gears here a little bit. Let's talk about the changes that were done on the graphics side. What is new when it comes to the graphics side for Lunar Lake?
Yeah, first it's a big graphics engine. Okay, so it gives the value by allowing creators and gamers much better user experience.
So our GPU is also a new microarchitecture, XE2. XE2 brings a significant performance increase and also improve our AI capabilities. It's integrating XMX engines, which take care of the AI usages. So overall, performance increase, scale to AI, and new microarchitecture.
So we have the graphics side, and you said we also have new like a media engine, a display engine. Can you tell us a little bit more about that one?
Yeah, so we have it's actually the media engine and the display engine are part of the XE2 architecture. It integrates HDMI 2.1 as well as DP 2.1. It also has a low power EDP 1.5 channel, which enables us good output as well as low power output.
Do you know how many display pipelines it has? Like how many monitors?
We have 3 display pipelines. And actually, I didn't mention, but we are also supporting the H.266 or VVC decoding, which is a major upgrade in our capability to decode capabilities.
And we still support, like because in Meteor Lake, we were supporting AV1 encode and decode.
Correct. We still support it, yes.
Okay, that's great. So that's pretty cool when it comes to all the graphics side. Let's talk about the NPU. This is the neural processing unit. And what's new in there?
Yeah, it's a major upgrade. We actually increased the number of tiles. We have 6 neural processing engines and 12 the shaped DSPs. Both of them improve AI acceleration significantly with 9 megabytes of cache. And actually the architecture improves power efficiency significantly. So the big claim for NPU is gets a lot of TOPS in a very low power, so it's very efficient. And by increasing the number of engines, we can run it lower for cases in which we are running background AI tasks or don't need high power throughput, and therefore it's very efficient.
Okay, so we have increased the number of neural core engines, and therefore we can do all those things.
Correct.
Okay, so those are all the different engines that we have in the compute tile. What can we find in the platform control tile?
So in the platform controller tile, we can divide it to two main functions, the security and the connectivity.
Yeah, we have three engines of security. We have the Intel Partner Security Engine, which is a new engine, and we have the Intel Silicon Security Engine, which is responsible for all the authentication stuff. And we have the CSME, which is the legacy engine, which is used for secure data from power on.
And from connectivity perspective, we have integrated Wi-Fi 7, which was the first time we are integrating the Wi-Fi 7 inside the chip. We have USB 4 and USB 3 ports. We have the PCI Gen 5 and PCI Gen 4 ports. And we have Bluetooth and Thunderbolt. And some other enhancement that we did, but basically this is the main functions of the PCD.
So we have the compute tile, the platform controller tile, and we have the DRAM, and they're all connected, where they're on the same package and they're connected through.
Correct.
Through Foveros, or.
Yeah, so we have the compute tile and the PCD tiles on a single Foveros chip, and we have DRAM packaged on the same package with them.
So compared to Meteor Lake, that there was also a NOC, a network on chip, right? That's the name of the bus. There has been a lot of changes done when it comes to Lunar Lake that you were talking. Mm-hmm. And one of those changes was that now like a unified protocol that it can actually talk to. Was that different on Meteor Lake?
So in Lunar Lake, we did a lot of changes in the interconnect. Also, we created a unified protocol and separated between the network layer and the protocol layer. We also improved the interconnect power efficiency. And second thing we did is what we call extended scalability. We have the ability to move IPs from between dies. This is also something that we created in Lunar Lake. We have this flexibility. The idea is that you can scale this architecture goodness to the next generation, regardless of the cut line between the dies. So you have fabric in the CPU die, you have the fabric in the PCD die, but in general you can switch IPs between them because these are the same fabrics. And this is something that we call extended scalability. It's like, for other segment, for other purpose, for different mix and match between process and cost, you can have this flexibility to scale the IPs. And by the way, we are taking Lunar Lake goodness to the next generations.
That's pretty cool because that means that you're not attached to one tile. You can move that block or that IP to a different tile, and depending on the process, so you're not tied to one process. You can just move it around, and it's like a Lego building block. Just like, oh, let me move it here, put it over here.
So you can think about it as IP agnostic and partitioning agnostic.
Yaron, thank you very much. Appreciate it. Learned a lot today.
Welcome.
Arik, I learned a lot today. Thank you so much. I appreciate it, man. This has been great.
Thank you very much.